a metric, the gauge field and the scalar. And we saw that for very low temperatures, we can actually predict the temperature dependence of the value of the scalar on the horizon. We can predict the temperature dependence of the entropy. Okay, so the temperature dependence of the entropy, that's something meaningful that you know already. I mean, from the thermodynamics point of view, that's something interesting. But today I want to tell you why we are also interested at the other characteristics of the horizon, right? So what is, for example, the value of a scalar field on the horizon? Why should you even care about that, okay? So before we do that, I want to talk a little bit about, let's say, linear response and quasi-normal modes. Okay? So at exactly T equals 0, at 0 temperature, you know, I mean, let's take some simple case. The retarded Green's function of some operator of dimension delta in a CFT, and I want to write it in the frequency and wave vector plane, wave vector space. So if the dimension of the operator O is delta, then you expect some retarded Green's function to look like this. Okay, you might be more used to the coordinate space Green's function, but if you Fourier transform, you will find an expression like this. Okay. So if I just look at this, I mean, and if I look at this two-point function from the omega point of view, you will see that this will have branch cuts. Okay, so at omega equals plus minus k, this retarded Green's function will have branch cuts in the omega plane. Now, at t not equal to 0, what black holes want to do is that they basically want to take a branch cut. Let's say that I had chosen the branch cut to be exactly on the lower imaginary axis, and they want to transform it to something like this. So they will basically resolve the branch cut into a series of poles. Okay? And the distance between the poles will be set by the temperature. And as I'm taking the temperature to 0, then these poles go very close to each other, and it just gives you something that looks like a branch cut, or a branch cut. Okay?
Yeah, I referred to these in my talk, and I said that you would probably explain this, but these are precisely the things that are responsible for the exponential decay in finite time correlators, and these quasi-normal modes that I mentioned here, precisely due to these poles. And now you'll hear all the details about these things.
Okay. Thanks, Jan. Okay, good. Good. So, and in fact, if you're wondering about the analytic structure of the Green's function at finite temperature, this is all you will see. Just a bunch of simple poles in the lower half plane. Nothing else. So, what can you write? So what you can write for the Green's function is something of this form. So there will be a sum over these poles. There will be infinitely many poles. If the position of the pole, of the ith pole as a function of k is omega I of k, right? So I will need to have exactly a pole when omega is omega I of k. And then in the numerator, well, you can have some analytic function of omega and k. Okay, that's all you can have. And now I'm converging more and more to what Jan just said. Good. Now, why do we care about the positions of these poles? So if you introduce a perturbation, by using this operator O, you basically deform the Hamiltonian of your theory. We are in D space-time coordinates, so the space-like coordinates will be D minus 1, and I have O of x, and delta H is the source parameter. Then I also want to define the Fourier transforms of the two-point function, right? So if in coordinate space the Fourier function is g t minus t prime x minus prime, then I can be careful with factors of 2 pi. So we'll have e to the minus I t minus t primed plus I k x minus x primed. And here I will have the Fourier transform. So this is the object, basically, that I have written here. Well, let me put a tilde, just to make sure that I'm talking about the same thing. And let me also introduce the Fourier transform of the source. Delta H tilde of omega and k. Now, the VEV of the operator O, we wrote this equation yesterday as a function of t and x, is going to be given by an integral g of t minus t primed x minus x primed times the source at t primed x primed. Okay, so if I plug in now the Fourier transforms, I can write this as 1 over 2 pi d, and then integral over frequencies over wave vectors e to the minus I omega t plus I kx g tilde of omega comma k, and then delta h bar of omega comma k. Okay, so now you see that the poles of this function, if I close in the lower half plane, which I cannot, if I close in the lower half plane, then these frequencies would basically pick up these poles. Okay? So if I do a simple example, let's take a simple pulse. So if in real space the source looks like this, so delta h of t comma x, let's say that you have something monochromatic. There is a function of time, which is like a step function, times some monochromatic wave vector, and f of t is 1/2 for t being between minus tau and tau, and 0 otherwise. Then the Fourier transform of this pulse, you might have seen this many times in your careers, is basically 2 pi to the d minus 1 times a delta function kp in k times a sine of omega tau divided by omega, right? So if I now take this finite pulse and I substitute it here, I will have that the VEV of the operator O as a function of t and x will be 1 over 2 pi. I can trivially do the integral over k, right? I have a delta function here. I will have an e to the I kpx times an integral over omega. And I will have sine of omega tau over omega times g of omega comma kp. Good. Now, if the Fourier transform of the retarded Green's function, I forgot the tilde here, had a finite number of poles, right? So I'm basically integrating like this. And if I had a finite number of poles here, I could just do that. Okay? So in that case, for t greater than tau, which means late times after the pulse is over, I can close, there will be an e to the minus I omega t here. There is some exponentials coming from this sign, but as long as t is greater than this tau, I can just close the circle in the lower half plane. Then I would get that delta of the VEV as a function of t and x would be 1 over 2 pi. And then a sum. So this omega that I have in this exponential here would be precisely evaluated at the position of the poles. And I is running over the different poles that I have in my Green's function. Okay? So this is the late time behavior that I would get if I had a finite number of poles in the lower half plane. You don't have a finite number of poles in the lower half plane, so this argument is not, strictly speaking, correct. But the late time behavior is still this. Okay, so this argument would give you some intuition about what should happen, and this is actually what is happening. However, this is not a proof, really, because you don't have a finite number of poles in the lower half plane. Despite that, at late times, the behavior is described by the positions of these poles. Okay? So what does stability require here? So you see, somehow, I need to go back to equilibrium, right? So the perturbation would have to fade away. I would have to go back to my thermal state, and if my thermal state did not have a VEV for O, I would go back to 0. So this means that stability requires that the imaginary part of these poles is negative. Otherwise, this exponential would not be decaying, yes. Okay, so I have, first of all, let me change the index because this is confusing. Okay, let's sum over J. This part?
J of K.
It's omega J of Kp. That's time. Sorry. I wanted to write time. I wrote something else, and I thought you understood what I wrote. This is T. Or a broken epsilon. Okay? So, right. The other thing I want to tell you is that for a generic operator O, the imaginary part of these poles is negative for all k. Okay, so all these modes are gapped. They have a gap. Whatever, I mean, no matter what the value of k is. I mean, as I'm varying k, these poles will start moving in this plane, but they will all stay finite, even at k equals 0. Okay? They all have a finite decay rate. However, I want to talk about these special poles, which actually go to the origin as I'm taking k to 0. So when should omega, I mean, one of these poles should go to the origin as I'm taking k to 0? Well, you can see that this corresponds to some conserved quantity, right? So it's not dying off. For some reason, my perturbation kicked this quantity. I added something to the system, and it doesn't want to go to 0, right? So when I take k equals 0, and this omega goes exactly equal to 0, then O corresponds to a conserved quantity. Conversely, all conserved quantities will give me some poles in the lower half plane, which will go to 0 as I'm taking k goes to 0. Okay? So these are the hydrodynamic poles. So the exceptions to the previous rule are conserved quantities, and Goldstone modes. Okay. So if I now draw, yes.
So somehow in the t equals 0 case, the choice of where we put the branch cut was arbitrary, right? Because if you have some complex function with some poles, you don't need to only have negative.
Yes.
But somehow what this
Somehow
argument
finite
is telling us
temperature picks
a particular.
It
somehow
picks.
finite temperature picks this.
There is no ambiguity in that.
But if we would have our choice in the t equals 0 case was the positive imaginary axis, and then you just put small t and suddenly all the poles go down to negative.
I think you would always want the branch cut to be in the lower half plane.
Yeah, that's what my question was, that in principle it's arbitrary, right? Like if you have just complex analysis point of view, where you put the branch cut.
You have some analyticity requirements in the upper half plane for the retarded Green's function, right? So the Green's function should be analytic in the upper half plane, which means that whatever nasty stuff you want to hide, it should go in the lower half plane.
Okay. Okay.
Okay. So the picture that you can draw after you have, after we have discussed these poles is that if you have hydrodynamic poles involved in whatever dynamics you are looking at, then as I'm taking k to be the smallest scale in the problem, by scale I mean chemical potential, temperature, whatever has a scale. If k is the smallest player in the game, then in general what you will have is something like this. So you will have these poles that want to stay, at some finite distance from the origin, even for small k. Okay, these are their own universe. But you will also have these poles, which are the hydrodynamic poles, which as I'm taking k goes to 0, they want to go very close to the origin. In fact, the closer your pole is, to the origin, the more dominant it becomes at late times. Okay, so the poles that are deep in the complex plane will just die off very fast. And what will dominate everything as you thermalize again is the hydrodynamic modes. Okay? So somehow, you want to have some effective theory which is just describing these dynamics. Okay? You want to somehow integrate out all this stuff, all this fast decaying stuff, and you want to have an effective theory that describes these modes. Okay? So, and this is hydrodynamics. Any questions? Okay, so what you might want, what you might notice is that as I'm taking k exactly equals 0, then the system looks like more like thermodynamics. Okay, it's somehow the k goes to 0 limit should make a very good contact with what we understand from thermodynamics. So thermodynamics is probably a good start to understand hydrodynamics. So let's go back to thermodynamics. Okay. So let's call this relativistic hydrodynamics. I will be very quick about this. I just want to extract a couple of things from it, right? So, right. So let's say that we are in thermodynamic equilibrium. And let's say that we are also in the rest frame. Rest frame means basically that the system has 0 momentum. I can always pick a coordinate system where there is no net momentum in the system, right? So in the rest frame, this means that the TT component of your stress tensor will be the energy, or the energy density epsilon, and the IJ component of your stress tensor will be the pressure times delta IJ. Now, for the charge density, for the conserved, if you have an electric current in your system, the time component will be the charge density, rho, and the electric current will be 0. Now, there is a little bit of an assumption here that I am not in a superfluid phase. Okay, so for superfluids, you can have 0 momentum, but you can have a non-zero current. How can we understand this? Well, in a superfluid, there is particles which are in the quantum mechanical ground state of the system, right? So these particles cannot carry heat. They cannot transfer energy, but they can still transfer electric current. But if you say that you don't have any, a big population of such particles in your system, then then you can assume that if you set the momentum equal to 0, you can also set the current equal to 0 at the same time. Okay, if you have a superfluid, well, that's the whole point of superfluids, that you can still have what is called a supercurrent. Good. Now I'm working in an ensemble, in the grand canonical ensemble, so the energy is to be thought as a function of temperature and chemical potential. The pressure is again a function of temperature and chemical potential, and the same thing for the charge density. Right, so this is just thermodynamic equilibrium. but you don't necessarily have momentum.
Okay. Why that is the case?
Right. So if you think of it from a mathematical point of view, you have what is called the fluid velocity and the superfluid velocity. These are two independent variables.
Okay.
You can choose a frame to set the fluid velocity equal to 0, but that doesn't necessarily mean that you have set the superfluid velocity equal to 0.
Okay.
Okay? And that could give you an electric current, but no momentum.
Okay.
Okay?
Thank you.
Good. Okay, so we are now in the rest frame, thermodynamic equilibrium. Let's stay in thermodynamic equilibrium, but let's just boost this. Okay, let's do a Lorentz boost. So in a generic frame, still thermodynamic equilibrium, the stress tensor can be written in terms of what you would call the relativistic fluid velocity, which is basically the Lorentz transformation parameter that takes you from this frame to this frame. Epsilon plus. You can define a projection operator, delta mu nu times P. And you know that the current will just be the charge density times the fluid velocity. Okay? And since all that U is a Lorentz boost parameter, U squared should be equal to -1. And the projection operator, delta mu nu, is eta mu nu plus V nu, V nu. This is still equilibrium. I haven't done anything, no dynamics yet. Okay? Now, I'm starting to do hydrodynamics, basically looking at the long wavelength dynamics of the stress tensor and the current density, if I say the following. So assume now that the temperature, the chemical potential, and the fluid velocity, u mu, become weakly space-time dependent. Right, so I'm promoting T to a function of time and space. The same for the chemical potential. And the same for the fluid velocity. And what does weakly mean? Weakly means that partial derivative, a space-time derivative, is on any of these functions is a small number. Basically, this is what I was calling small k there, right? So small wave numbers means small derivatives. Okay? And now you might be interested in looking at perturbations like this. So the temperature, you might want to write it as your thermodynamic temperature plus a small fluctuation away from it, a space-time dependent fluctuation. The same for the chemical potential. Nu naught is the thermodynamic chemical potential plus a small fluctuation. And the same for the fluid velocity. Again, this is some small number. And delta T, delta mu, and delta V are also of order epsilon. Okay, they are all small numbers. So both the derivatives and the amplitudes of these fluctuations are kind of small. Okay. Any questions? Yes.
It's the epsilon, right? Just to confirm.
Thanks for asking. No. Another Greek letter, delta. I like delta. No, I have delta.
Don't worry about it. You don't need to change it.
Is it fine to everyone? Yeah. So this epsilon is not that epsilon, okay? Thanks for asking that. Yes.
I mean, going back, sorry, to the graph that you put in there. Yeah. Because you mentioned, I mean, there are different parameters that describe, in this case, the model that you are analyzing, right? Like temperature, the chemical potential, and whatever. And I'm still having a difficult time trying to grasp the idea of what is this idea of the smallest one, the smallest parameter, or the, that's still confusing me.
You mean how,
yeah,
about this K?
Yeah, I mean, I understand that K could be T, could be the chemical potential, but what I don't understand, because you said the smallest one.
Sorry, that K is supposed to be the wave vector of the dynamical perturbation, right?
Okay.
It's a specific number.
Okay.
So I'm saying that this number should be the smaller parameter in the problem.
Okay.
Okay, well, as you compare it to temperature, what other dimensionful parameters do you have?
Okay, so that's
temperature,
already
chemical
set
potential.
Up in the, okay, I see.
Okay?
Thank you.
Thanks for asking. Any more questions? No. Good. So at this level, what do I want to do? Right. So the thing I want you to notice is that I have parameterized the stress tensor and the current by using how many parameters? So I have one, how many dynamical parameters? I have one for T, one for mu, that's 2. I would say that I have D for the fluid velocity, but the fluid velocity has to satisfy this constraint. Okay, so that's really D minus 1 numbers coming from the fluid velocity. So in total, I have D plus 1 independent functions, or dynamical functions. They depend on space and time. That is very nice because these quantities, the stress tensor and the electric current, they satisfy the word identities. Okay, so I know that I could, if I am in flat space, I would have to solve these two equations. Now, if I count equations, I have D equations from the stress tensor word identity and one equation from the electric current. Okay, so that's D plus 1 equations. So now, the word identities, which are in general not a closed system of equations, becomes a closed system in terms of these variables. Okay, so now I have some equations to solve, basically, and which would tell me something meaningful.
The definition of the temperature and the chemical potential is actually not unique if you're talking about hydrodynamics. So doesn't that affect the number of variables you have?
Later. Not yet. Well, that will affect the corrections, I mean, which I will talk about later. Yeah. So the question is, so this is not unique. I can always change the definition of what I call T, mu, and V. But that will push things at higher order in this derivative expansion. Okay? And when we talk about corrections to these expressions, yes, we will see that there is a finite number of, there is a specific number of parameters that you need to parameterize those derivative corrections, modulo transformations of local transformations of chemical potential, temperature, and fluid velocity. So yes, I will have to impose some conditions on these things, but we will see that later. Okay, so that's now a closed system of equations. Right. So let's perturb the components of the stress tensor and the current and let's see what we find. Should have it here, I think. Right. So delta T T T would basically be just the perturbation of the energy. And you can use hydrodynamic relations, thermodynamic relations, to write this as background chemical potential times the charge susceptibility times delta mu plus another susceptibility times delta T. So this susceptibility psi is basically the derivative of the charge density with respect to temperature plus the temperature times the same susceptibility psi, and this is coming from the derivative of the entropy density with respect to the chemical potential, but you can use Maxwell's equations and you can show that this is actually equal to that, Maxwell's relations, and so these numbers are going to be the same here. Times delta mu plus temperature to the -1 times heat capacity at fixed chemical potential times delta T. Now you can do the same thing about the Ti component of the stress tensor, and you will find Ts plus mu rho times delta Ui, and delta Tij is delta Ij times variation of the pressure, which will give you charge density times delta mu plus S times delta T. Now the variation of the charge density is going to give you the charge susceptibility times delta mu plus psi times delta T. And the variation of the electric current is going to be the charge density times delta Vi. Okay? Now you can plug this system, this expansion of components in those equations, and that will give you a system of equations for delta T, delta mu, and delta Vi. Now, you can do that, and you will get a pretty awful system of equations, which I don't want to deal with right now. But I want to specialize to some case which will also help me for later. So if I look at a system which has no background charge or no background chemical potential, yes?
When you're varying the TT component,
yes.
Why not varying also the fluid velocity?
Over here?
Yeah.
Okay, good. So I'm saying that, okay, so U mu, so U T has a background value, okay? But the perturbation still needs to satisfy this. Okay? So the perturbation is basically telling me this. So delta ut would be 0. Okay, so I don't have to vary delta ut. Is that everything clear to everyone? Thanks for asking. Yes, good. Okay, so if I plug in now this into that, I will get some equations. But I want to focus on a much simpler system, you know, which is at 0 background charge density or 0 background chemical potential. Now, if I do that, you will see that the dynamics of local temperature and the local fluid velocity are governed entirely by the word identities for the stress tensor. And the dynamics for the chemical potential, I mean, this guy will go away. Psi is 0 at 0 chemical potential. And then, and also rho, the background rho is 0. So all the dynamics will be governed basically by the current conservation, right? So let's just focus on that case, the neutral background case. So for neutral fluids, where is it? Right, I have rho equals 0, nu equals 0, and psi equals 0. Now, in this case, the word identities are going to give me 3 much simpler equations. So we'll get that chi times the time derivative of the variation of the chemical potential is 0. That's the current conservation. So the time component of the word identity will give me sim nu times the time derivative of delta t plus s times the divergence of delta v is 0. And that t times the time derivative of delta v plus the ith derivative of delta t is 0. Now, very quickly, from this first equation, and at least at leading part in derivatives, this is what we call the charge diffusion mode. Charge diffusion. Okay? Now I still need to deal with the system of the other 2 equations. So the other 2 equations can give me a second solution. So if I take a time derivative of the first equation and the divergence of the second equation, and I combine those 2, I will get that sim nu times the second time derivative of delta t minus s over t times partial I squared on delta t is equal to 0. Okay? So this is giving me now a pair of modes with frequency omega squared is s over t sim nu k squared. That's a closed system. So this is called the sound mode. Okay? So I can also write this as omega squared is the speed of sound squared times k squared, where the speed of sound squared is entropy over T times the heat capacity of the system. And now there is a third mode that I can find, or maybe a third class of modes. So the third class of modes have delta mu equals 0 and delta t equals 0. And they also have a divergence-free fluid velocity. And moreover, I will get that the fluid velocity is independent of time. Okay, so if I think of wave vectors, basically it is telling me that the wave vector has to be orthogonal to the fluid velocity, right? So all the variation in space is happening orthogonally to the fluid velocity. And this is d minus 2 shear modes. So this leads to d minus 2 shear modes. Which have omega equals 0. And also the charge diffusion has omega equals 0, right? So it is telling you that the chemical potential has to be time independent. So in total, what we have discovered is 3 kinds of modes. So the first mode is the sound mode, which looks something like this. The second one is the charge diffusion mode, which starts with a 0, and there will be corrections. And then there is the shear mode, which starts again with a 0, and there will be corrections. Okay? So at this level, just by thermodynamics arguments, you can see that these modes at finite k will never die out, right? There is no decay component in this at this level. There is no dissipation. Okay, all omegas, these are the omega i's, right? So these are the positions of the poles. So what I have discovered is that if I just go with the ideal part of this fluid, I will never find dissipation. So these modes will never die out. Yes? Can you repeat? Oh, here, sorry. Yes. That should be a time derivative. Thanks. Good. So let's now discuss the derivative corrections of these, of whatever I'm doing. So at this point, it's just thermodynamics, right? There is no new input. Yes?
That's a wave equation,
That's
right?
the wave equation, yes.
Where did K come in?
Where did K come from?
Yes. Is it in momentum space or something?
Oh, yes. I have now Fourier expanded delta t, e to the minus I omega t plus ikx.
Sorry, okay. I missed that part.
And yes. It's a standard thing that you would do with a wave. More questions? Yes. The indices of the vector. Sorry, yes. So this is supposed to label different modes, right? So this is sound mode, S. This is charge diffusion, CD. And this is the shear mode. Which one? Charge diffusion. Okay. You don't see any diffusion yet, but you will. Okay, so good. So we made an assumption that things will now start depending on derivatives of what we called local temperature, local chemical potential, and local fluid velocity. And you might want to start correcting the relations between the stress tensor and the currents, and these local quantities, T, nu, and V. So let's talk about derivative corrections and dissipation. So let me write again the first part that we wrote, the ideal part. Plus a piece which can in principle contain derivatives of u, derivatives of t, and derivatives of nu. Okay? So when I am exactly at thermodynamic equilibrium, since it only contains derivatives, I know that this piece will go to 0. Okay? And I will get back my ideal fluid at equilibrium. And let me do the same thing about the current. So I will have my ideal piece. And let me call it little j, or j2 nu. Now comes the question that you asked before, right? So look, you can say, okay, so we found some solutions. I mean, these solutions, right? So these functions have to satisfy some equations. Okay, but I can always take these solutions and make the following shifts. So I can take t to what I had as my original t, my original solution, and shift it by some function. I can do the same with nu. Sorry. I can do the same with nu. And I can do the same with v. I can plug in my solution that I found from there. I can just shift things. And as long as these functions are order epsilon, then I cannot distinguish whatever I call the solution from just a shifted solution. So at the level of ideal hydrodynamics, this is not going to have a big effect. However, if you look at this expression, if I shift any of these functions, right, p, or I mean, if I shift delta t, and consequently, if I shift this term epsilon by shifting delta t or delta mu, or that term, then I'm basically changing the definition of these two guys. Okay, so whatever I write down at some order in epsilon, I can always do a transformation to the leading order hydrodynamics, and I can change the definition of these two things. Okay, so this is telling you that you basically need to fix a hydrodynamic frame in order to write down some meaningful expressions. We all have to agree what these functions are supposed to do at the end of the day. So how many functions do I have free? I have 1, 2, and since this will always have to be norm 1 vector, you know, I always have this condition on whatever transformation I can do. And so I need to fix d plus 1 conditions in order to give you some meaningful definition about these corrections. Okay? Now, it turns out, I will just write down the answer, that if you go to what is called the transverse frame, which is pretty standard, okay, so you can fix what is called the transverse frame. There is many frames, and there is many different choices. I happen to like this one. So in the transverse frame is basically defined by some projection conditions. So these are D conditions. There is one free index nu. And there is one more condition on the electric current corrections. So as long as you impose this, there is then no freedom in redefining the local temperature, chemical potential, and fluid velocity. So what can you show? You can show that all you have left to parameterize these corrections is 3 numbers. So the first number is called eta, the shear viscosity. Sigma mu nu is a tensor that you can write in terms of V. I will write it down. And then there is another number which is called the bulk viscosity. And it comes together, of course, with a derivative of the fluid velocity, right? So we said that T mu nu 2 can only depend on derivatives of V, T, and mu. Yes? V?
Yeah.
Oh, here, this one.
Yes.
Yeah, sometimes I write V, sometimes I write U, sorry. Right, so delta U, I would call it, yeah, delta V, yeah.
Okay.
Sorry.
That clarifies it. Thank you.
Okay, yes. And for the electric current correction, there is a third number, which is called the incoherent conductivity. Delta mu nu. And partial nu over T. And then sigma mu nu, the shear tensor, is delta mu alpha, delta mu theta, times partial alpha u beta, plus partial beta u alpha, minus 2 over d minus 1 and alpha beta partial lambda u lambda. Okay, so sigma mu nu is traceless, and it also satisfies, I mean, if you contract with u, because you have these projection operators delta, you will get 0. Okay, so I mean, the property to keep in mind is that u mu, by construction, delta mu nu is 0. Any questions? So now you see that these derivative corrections are introducing 3 numbers. Okay, so eta is the shear viscosity, zeta is the bulk viscosity, and sigma is the incoherent conductivity. Okay. Now, if I'm not breaking scale invariance or Weil symmetry from the field theory point of view, and because the strength tensor has to be 0 for any configuration, you can show that zeta should be 0. However, we are deforming the theory. I mean, we are introducing many scales. There will be a non-zero bulk viscosity. And this eta, even from the holographic point of view, I mean, it has to be there and be non-zero, okay? Now, in terms of physics, what I wanted to show you is this nice, cool thing. Now, if you look at the expression for J, this rho v is what we usually learn at school, that you have some charge, you give it some velocity, you will get a current, okay? However, that mechanism over there is telling you that even if you don't have a background charge or a background chemical potential, and you have variations in the chemical potential in your theory, and even if you don't have any net background charge, you can still get a current, okay? How can you think about this? I mean, you can probably think of it in terms of, I don't know, particle anti-particle creation, right? You don't have any net charge, you will get two particles of the opposite charge moving in the opposite directions. You will get a net current, even if you don't have any background charge density. So this is really a new mechanism that your system can transfer charge or carry electric current. And this is actually a way one of the ways that a system can violate what is called the Wiedemann-Franz law. Okay, so having this as a non-zero quantity, having a non-zero sigma, will in general violate the Wiedemann-Franz law. Okay. Right. What else do I want to say? Good. So after you correct these the constitutive relations, you can go back and solve the word identities once again, and these relations will be now corrected, right? So you will have higher order in k terms, and the corrections you will get. I mean, I will not go and solve this system again. I will just write down the corrections. Good.
So in that gradient, so like an expression for J mu 2, there is like this gradient of mu over T, with mu being a chemical potential, right? Yes. Didn't we set it to 0 at the beginning of the derivation?
We set the background value, but not the fluctuations.
Okay, so it's a okay.
Okay, so
it
a
should
partial.
Be like there is like the d delta mu then.
This one? That's a derivative.
No. I mean like the mu in the part inside the. So it would be what we call delta mu or something like that.
Right. So there will be two terms, right? There will be the derivative on t times mu. That will be 0. But the derivative on mu, that's non-zero, because it will be the fluctuation of mu. Thanks for asking this. Yes, that's.
Is there a this seems, especially the current one, J2, seems like a very particular structure. Like, I could get the Lorentz structure is fixed somehow by symmetry, but like, is there something fixing the particular way that T and mu must come into J here?
These transformations, basically. You can show that if you had some other, I don't know, partial T there, right? Some other combination of partial mu and partial T there, you can show that you can just eliminate it by these transformations. You can go to a frame.
Yeah, I just mean that you like the U and J being orthogonal, defining the frame. Like as long as J2 is proportional to delta, then that will be satisfied. So surely you should be able to put any random function of mu and t there and still stay in the transverse frame.
Right, but I can make a transformation, right? I can still transform mu, I think. Or I can change v, right? Right, so the leading part is this. So I can change u by derivatives of t, or derivatives of mu.
Right, right, yeah, sure. Okay. Okay, cool.
Okay.
Thank you.
Good. good. So if you go back and you solve again the problem, I mean, just no background charge density, then the speed of sound, I mean, the sound mode dispersion relation will be modified to plus minus speed of sound, the norm of k, and now you will get your first correction. Times 2 d minus 2 over d minus 1 times eta plus zeta, plus now higher order terms, which I mean, I can keep correcting. I can add second derivatives, third derivatives, and that will always be correcting these dispersion relations. Okay. What do I want to write? So the shear mode will now start becoming more non-trivial. And the charge diffusion mode, the same. Okay. Good. So you see that as soon as I start correcting my dispersion relations, now I mean, these modes will start going down in the lower half plane, and I will start getting non-zero decay rates. Still, when I take k goes to 0, all three modes go to the origin, okay? So, which is exactly what we were expecting to see, or hoping to see. Okay. Now, what do I want to get from holography? So what holography, I mean, as long as you are looking at this ideal part of the fluid, I mean, there is nothing to ask in holography. It's just energy, pressure, charge density. Why would you want holography, right? So if you ask the question of long wavelength dynamics within holography, what you might want to fix, or what you want to fix, is these three numbers. Okay, somehow these three numbers that I introduced and which are responsible for the dissipation in the system are going to be fixed by holography, right? So that's what you want. Are we all together somehow? Yes. Okay, so now I will do a very simple system. I will just look at neutral black hole backgrounds, and I will study the dynamics of the current density, hoping that I will be able to extract what this sigma is. Okay? Good. So somehow, I need to start creating a hydrodynamic perturbation within holography. Okay. So what was our theory? I will write down the usual theory that we have. I mean, in these lectures, in coherent. Okay, so right, so the background geometry that describes our black hole is this. So we have this metric. And let me focus, I mean, in the case of ADS4, just 3 boundary directions. Space-time directions. For thermal conductivity. Not in a relativistic theory. Right, you can just by a frame. I mean, even if you introduce a coefficient there, you can again set it equal to 0 by fluid frame transformation. Okay. Right. So the background Gates field, we are looking at now neutral black holes, right? There is no background Gates field, it's 0. And okay, there is some radial function of for the scalar field. What did we say? So we said when we discussed black holes, we said, or black brains, we said that there is a horizon at r equals r plus. And then this function f of r close to the horizon goes like 4 pi t, where t is the temperature, divided by r plus squared times r minus r plus. G of r goes to a constant, some horizon value for g. And phi close to the horizon goes to like phi h plus some Taylor expansion, okay? So now to study the dynamics of the current from the boundary point of view, I need to examine perturbations of the Gates field in the bulk, okay? So the perturbations of the Gates field will be solving the equation of motion that we had written down. So G, Z of phi are just background functions, but I will have a small field strength because I'm looking at the perturbation. Now I want to write a perturbation for the bulk Gates field in a Fourier decomposition times a mu, where a mu is a function of the radius. That could be a good start. But I don't want to do exactly that, because as I'm taking the radius close to the horizon, t is not a well-behaved coordinate. Okay, I have to do something slightly better than this. I have to improve this. So how can I improve this? So instead of writing this, I will write this. Omega of t plus some function of the radius plus ikx, this is all in the exponent, times a vector which depends on the radial coordinate. Now, what is this function s of r? So s of r can be anything I like. Okay, I haven't solved anything. I just wrote down some answers. But I want S to have a specific behavior close to the boundary and close to the horizon. So S of R should be going to 0 very fast at r goes to infinity, close to the boundary. Now, close to the horizon, which is at r plus, s of r, I want it to go like the log of r minus r plus divided by 4 pi t, plus other stuff. Okay, so the most singular behavior of s close to the horizon, I want it to be this log. Why? You see, what I want to happen in this exponent is that t plus s of r goes like t plus log of r minus r plus divided by 4 pi t, as I'm going very close to the horizon. And this is really the ingoing Eddington-Finkelstein coordinate. That is a regular thing. As long as your function, this function, goes to something analytic on the horizon and s of r has this behavior, as long as you achieve this, then this will satisfy ingoing boundary conditions on the horizon. Okay, so this s of r function is designed so that you will satisfy the correct boundary conditions on the horizon. So what happens to the horizon if I go to this boundary condition, to these coordinates, right? You might have seen this, but I want to remind you. So the s squared close to the horizon will go like g8 times minus 4 pi t r minus r plus dt squared plus the r squared over r minus r plus 4 pi t plus the horizon part, which is not super interesting. And now if I go to this v and r coordinates, I will have g8 times minus 4 pi t r minus r plus times dv squared plus 2 dv dr. Okay? Now what I want to tell you is that dt is not a good one form on the horizon from the relativistic point of view. What is well defined on the horizon is dv and dr. Right? So exactly on the horizon, these one forms are very well behaved. Okay, so after this propaganda about dv and dr, let me see what the gauge field should be doing close to the horizon. I mean this gauge field, not the gauge field, but this one form. Okay, so now for the perturbation, this delta A mu, now delta A t close to the horizon should go like a constant plus another constant. These two are basically constants of integration close to the horizon. Plus whatever. Now, for the radial component, I can choose the following. Delta AR 0, some number, over 4 pi t r minus r plus higher order terms. And for the x component, it will go like a constant plus higher order terms. Okay? Now, regularity demands that the AT and the IR components will combine in a way that I will get dV. Okay? Otherwise, that would be singular. So regularity demands that delta AT naught is equal to delta AR naught. Okay? And then if I look at the Gates field close to the horizon, I will have that delta A would go like e to the minus I omega v plus I kx times this number, delta AT naught, times dv plus delta AX naught dx. So this is all regular, as long as I impose these boundary conditions, okay? Now, from the boundary point of view, I want to examine a perturbation that has no source, okay? When we did hydrodynamics, we didn't have any sources. We just looked at how a mode decays, basically. How a classical mode decays. So from the boundary point of view, whatever delta AT will be, it will have to go like minus delta rho over R. Delta AR should go to, delta AX should go to delta JX, where delta JX is the current over R, and delta AR should go to something really, something that decays really fast. Okay, this is for a general perturbation, right? So I haven't done anything that would tell me that this is now a hydrodynamic perturbation. This is just in general, just studying a general perturbation of the Gates field. Now, let's start creating a hydrodynamic perturbation. So what is the requirement for a hydrodynamic perturbation? So if I take both k and omega in this perturbation equal to 0, this delta A mu that I had written should go to a thermodynamic perturbation, right? To some static perturbation which is basically becoming thermodynamics. So a thermodynamic perturbation, a small thermodynamic perturbation, I know one. It is the one that adds charge to the black hole. Right? So we know that we can add charge to these black holes. And a static thermodynamic perturbation will go like this, close to the boundary. So it will have a small chemical potential. It will have it will add a small charge density, and it will have some subleading terms. Now, for small delta mu, what this delta rho is basically the charge susceptibility times delta mu, okay? So I can also write this as delta mu minus the charge susceptibility of the black hole at 0 charge density times delta mu over R. plus other stuff. Now, close to the horizon, the thermodynamic perturbation is going to look something different from that. Because we said that the gauge field, I mean, the time component of the gauge field should vanish at the horizon, right? So this real-time perturbation is slightly different. It's not the same thing. So from the horizon point of view, and if you use charge conservation or Gauss's law, you can show that this is equal. I mean, it doesn't matter. It will be some number, delta A naught thermal, times R minus R plus, okay? Plus something. However, if this is the limit of the omega goes to 0 and k goes to 0 perturbation, I am in a bit of trouble because I have a source here, and I don't want to have sources. Okay? So now I'm going to do a gauge transformation, which is like the gauge transformations we were discussing yesterday, and basically remove the source from the infinity. But the gauge transformation I'm going to do is going to be of the following form. So I will take a mu, and I will add to it a gauge transformation, lambda. And lambda, I'm choosing it to be minus delta mu times t plus s of r. Why am I doing this? So you see that this is going to shift the time component by minus delta mu, so that is going to kill this term. Okay? And I'm adding this function s of r because I want the gauge transformation to be regular close to the horizon. So if I just had t here, I would have a singularity at the horizon. If I combine it with this function s of r, I'm going to get the ingoing Eddington-Finkelstein coordinate. Okay? So that lets me write down a static solution, which is basically the thermodynamic perturbation plus this gauge transformation. Okay? That's the zeroth order solution. Now, to construct the hydrodynamic mode, I'm going to write the perturbation of the gauge field in the following way. So I'm going to introduce a scale epsilon, which multiplies omega. And the scale epsilon should also multiply k, the wave number. And this is going to now start with this static perturbation. And it will also have epsilon corrections. Okay, so as I'm increasing epsilon from 0, I'm going to be correcting this solution. I mean, this one. Static mu. Times, let me call these corrections delta AL. And so the goal is to now go back to the equation of motion. I know that this is a solution at exactly epsilon equals 0, and start correcting the system, by constructing these solutions. Okay? Now, you can start doing this perturbatively. I think I want to skip most of the details, or maybe all the details. But at the end of the day, what you will discover is that the current that you will read off from the boundary has a very specific form. I mean, just by solving Maxwell's equations in the bulk and extracting the currents at order by order in epsilon, then at leading order in epsilon, what you will read off from holography is the following. So JT, which is the charge density, or the time component of the conserved current, is chi delta mu, okay? This is exactly what we wrote here. I mean, that's coming from the leading order perturbation. For the current, for the transport current, the first correction you will find is minus Z as a function of phi evaluated at the black hole horizon times the x derivative or the ith derivative of delta mu. Okay? Now, this is exactly what you wanted to see to read of sigma. Okay? If you look at what I have from hydrodynamics here, is that sigma is whatever multiplies the ith derivative of mu. So this is telling you that sigma, the incoherent conductivity, is going to be given by this function zeta, z, that you have in your bulk action, evaluated exactly on the black hole horizon. Okay? So the transport coefficients, basically, that you have introduced in dissipation, in hydrodynamics and therefore dissipation, can be read off by just looking at the black hole horizon. Now, I might have discussed just sigma at 0 chemical potential, but you can also do the same thing for the shear viscosity and the bulk viscosity. And you can write down some expressions. So at non-zero chemical potential, sigma basically becomes St, where S is the entropy density squared, divided by St plus mu rho squared times this function Z, evaluated on the black hole horizon. For the shear viscosity, I guess you will hear more about that from Carlos Hoyos. It's the entropy density divided by 4 pi, which is a pretty universal thing for holography. And for the bulk viscosity, you can write entropy over 4 pi times entropy times the derivative of the value of the scalar field evaluated on the black hole horizon plus the charge density and then the derivative of the bulk scalar field value on the black hole horizon with respect to the charge density squared. Okay, so if you know exactly how your black hole horizon looks, I mean, just the scalar field as a function of the thermodynamic parameters, then you can read off all the transport coefficients from the dual field theory point of view, which is a pretty non-trivial thing. And if you know how these functions behave at low temperatures, which is what we discussed yesterday, then you know how these transport coefficients will behave when you're very close to the ground state. I think this is the story I wanted to tell you. Thank you.